And so this plot here is the intensity of that siren as I'm standing outside of the sub by Chick-fil-A as a function of time. And I went ahead and doodled over it. There's like a low frequency curve you can kind of see, and then within those curves there are like high frequencies. But even then, these are pretty complex peaks, right? So like if I was going to ask you to find all the frequencies in that, you'd never be able to do it, right? Because they all superimpose over each other. So if you take the Fourier transform of this, which I did on my phone, you guys don't appreciate this, but do this when I was in college, which wasn't that long ago. I graduated in 1998. None of you were probably born yet. Maybe you were. But if you did to say I'm going to go do a Fourier transform, you had to go down to the basement and use like a supercomputer in the department to do a Fourier transform. It took like an hour. My phone did this in real time. So the fundamental or largest peak, that low frequency peak, is right here. It's actually a slightly flat of a B flat musically. If you want to think about it that way, or an A sharp sharp. I don't know. And so I just want to point out, and then these are harmonics next to it. So the point of a Fourier transform, and then by the way, this is like noise, like the noise background in decibels. So the peaks above it are all harmonics of that siren frequency. Okay. I bring this out just to show you that it's the same exact data. In fact, you can take Fourier transform data, do what's called an inverse Fourier transform, and recreate the time-based data. So this is the inverse Fourier transform to get this kind of data. So you can do this back and forth. Fourier transforms are used a lot in analytical chemistry. We use them in infrared. We use them in NMR, which we will never discuss again. I just said NMR the one time in class. Okay. And then in mass spectrometry, they're used all the time. But I thought this was like kind of a neat and totally nerdy real application. I was, and I say nerdy, I'll own it. I mean, you're all nerds because you're in this class. I'm sorry. You may think you're a badass, but you're like a badass nerd. Michaela and I both asked for TI calculators for a significant Christmas or birthday event when we were kids. How many of you asked for and or got a sweet, badass graphing calculator for birthday or Christmas in your lifetime? Just a few of us. Then you know the joy, right? Other kids wanted Transformers and things like that. I wanted a TI-81, and I still have it. It's seen better days. So this is kind of nerdy, but again, it just points out that Fourier transforms are actually pretty useful, right? Now I know I can go outside and like play along with the siren next month when they test it, okay? Well, let's get back to plasma sources, okay? Plasma sources are different than flames and laser sources in that well, first off, what is a plasma? Do y'all even know what a plasma is? Some people say it's the fourth state of matter, but they're wrong, in my opinion. But what is a plasma in general, just generically speaking? Does anybody know? It's a if you didn't get that, Aldo, I was going to tell you, a research advisor. Yes, because you should know that. It's a partially ionized gas, okay? It's not a fourth state of matter, but it has different behavior than a regular gas, right? Because while it should ostensibly fill its volume, you can confine it because it's got charged particles, right? But it's a partially ionized gas. It's actually a soup of atoms, ions, and electrons with sufficient kinetic energy, okay? So they're different from flames, but they have a lot of thermal energy. In other words, heat. So I can use them to generate excited state atoms just like I could in a flame. But unlike a flame, they're less reactive, they're spectrally simpler to use, that kind of thing. So we'll start off with glow discharge. I'm not going to talk about all the plasma sources out there, but two you're going to encounter in the wild pretty commonly, right? This is how hollow cathodes work. So we already have some familiarity with hollow cathodes, right? Ionized gas. Those ions slam into a cathode and then sputter off atoms of the cathode material, some of which are excited and emit light, correct? Okay. We can do that in a hollow cathode lamp, or we can do it with other samples. So in a glow discharge, we have a sample Now, there's two kinds of glow discharge. We'll talk about DC glow discharge first, or just in general. We have a sample, and it's conductive. It's a requirement in this case. Then we have a buffer gas inside this chamber. So we're in some kind of like box, if you will, for lack of a better term, with a window so we can measure light. And this buffer gas is going to be argon or neon, something like that. Sometimes helium if you're feeling excited. And we'll have an anode somewhere. Could be a ring, doesn't have to be. And the cathode is the sample itself. And so just like before, you create argon ions. I like the blue. They slam into the surface, and you eject atoms of the cathode material. This is your sample. These are excited, so guess what you get out of it? Photons from the cathode atoms. You also get photons from the buffer gas and the ions that it produces, but we know what those are, so they're easy to remove, right? It's like a blank. Like if I'm using argon, I know the argon emission lines, I just don't measure them, okay? And so this is a pretty straightforward process. The nice thing about glow discharge is it's a relatively simple approach, but also you can do something called depth profiling. Because sputtering removes layers. Does anybody here, anybody like cake? The food? Yeah? All right. So in a typical like birthday cake or wedding cake, you've got like a base of spongy cake that nobody really likes, and then a layer of icing, which is where the party is, so to speak, and then a layer of, you know, spongy cake, and then more icing, and you can do that multiple times, right? But there's like layers. You can imagine that if you were to like scrape off the first millimeter of cake, what is it going to be made out of? It's frosting or icing, right? Or fondant, which is not food. Okay, it's disgusting. And then you go another millimeter, you still got icing. Maybe 7 or 8 iterations of that, you might hit that first layer of cake, right? Finally, just scraping off layers. So if you think about it, I'm just going to give you an example here. Let's say I had a piece of metal, or a sample, that had a layer of titanium, and then a layer of nickel, and a layer of aluminum, just for fun. Okay. And then I've got argon ions, let's make them blue, hitting that surface, slamming into that surface. Okay. They're going to eject, if you look as a function of time, if I look at the emission for titanium, so in other words, I pick an emission line of one of the titanium, transitions I'm interested in, and if I plot a nickel emission and aluminum, just for fun, right? As a function of time, and these are the exact same time graphs, they start at time 0, I'm going to start seeing some type of titanium emission that's going to die off when that layer is chewed away. Overlapping that, I'm going to see in time a nickel emission that then kind of plateaus and then dies off, and then later on in time, aluminum emission, right? Now, what kind of samples would you ever find that have stratified layers like that? Well, how about sediment, right? You could certainly look at mineral profiles this way as a function of depth. And when talking about sediment, depth is a function of time, right? Like geological time. You could look at layers of human hair, right? Like the outer versus inner layers of hair. This is a big deal, or a bigger deal, in mass storage devices, because hard drives used to be made out of layers of magnetic material. The bigger ones still are, right? They're not all solid state yet. So you can take a hard drive, like platter or layer, put it on there, and then chew through the magnetic layers to make sure everything is right. This is a destructive process, right? The hard drive doesn't come back out, okay, there's a hole sputtered into it, right? But it's a nice way of doing depth-based measurements, okay? Your sample has to be solid, should be conducting, unless you can do RF glow discharge, which would be a non-conducting sample in that case, or less conducting. But there's another plasma source which is currently the most common, and that's the inductively coupled plasma. I say it's the best emission source only in the sense that it's the most common and it's good for a lot of applications. In this case, we use an argon gas to create a plasma. And so the way it works is the following. You've got a a quartz tube, and you flow, and I don't know why I make argon blue, I just do. You flow argon gas into it. Argon gas is pretty inert, right? Coiled around this tube is just a few turns of copper that's a radio frequency coil. It's just a coil that we apply an alternating current onto. That alternating current happens to be at radio frequencies. And so then what we do is we take one single electron and we add it. Now, in reality, we add more than one electron. We just have a little spark source, right? But you only need one. An electron is a charged particle, correct? I'm glad. Thanks, Jackson, for nodding. Somebody had to nod, otherwise I was just going to leave. Give up. Yeah, it's a charged particle, right? And in this electric field, in this alternating field, it actually oscillates back and forth. So the electric field causes that electron to sort of oscillate in some pattern, right, based on its mass and the field strength and everything. Well, the electron flies around, and it hits argon atoms and creates argon ions and electrons. Now I've got two electrons, right, because I have the electron left over still. Those two electrons hit two argon atoms, and now I've got two more electrons, right? So it creates a cascade, if you will, or an avalanche of charged particles. And so I end up creating a really pretty looking blue plasma. It's inductively coupled because you use induction from that coil, right, to create and sustain the plasma. It atomizes very efficiently. Right, so it creates a lot of atoms. It ranges from 6,000 to 10,000 Kelvin. Much hotter than flames can produce. Flames, suddenly an oxygen flame can maybe hit 4,000 Kelvin under the right conditions. So these are very hot sources. And if you go back to that equation for the Boltzmann equation, right, where you have the ratio of the upper and lower states, it's equal to the degeneracies, which are constant. Then this exponential term of the transition energy, Boltzmann's constant, and the temperature, right? So more temperature equals more excited state atoms. And that equals more signal, in this case, for emission, right? The emission's coming from an excited state to a lower state, so I need N1 over N0 to be a large value, right? Does that make sense? That's one of those intuitive steps you have to grasp before you move forward. So if you're totally lost, now is the time. And please never hesitate to raise your hand and be like, I totally don't get it. People may laugh at you. They're just being douches, right? Sorry. It's true. I will not laugh at you, and that's the important thing. Okay? The nice thing about ICP emission is that you can measure multiple analytes at once, right? So you can, have some well water and wonder what different elements are in it. Just take the sample and run it. You don't have to look for a specific element because you're kind of catching them all, right? So it's useful for a lot of things. Atomic emission is really good for qualitative analysis in that case, right? But there are other atomic methods. And I'm going through them pretty quickly because atomic methods are pretty mature and I think fairly simple to grasp, right? So the next atomic method I want to talk about is atomic absorption. Now, it's a very specific method. Now, when we say something is sensitive as a method, what do we mean? Like we're talking about sensitivity. You said low noise? I mean, not necessarily. Noise and sensitivity are separate, although low noise is good, right, for having a sensitive method. But the sensitivity in general is the slope of the calibration curve, right? So it's the response of the signal as a function of concentration, right? So when we talk about sensitivity, obviously we want a large sensitivity and, as Jordan pointed out, low noise, right? When I talk about specificity, what does that mean? If I may use one of my favorite analytical devices, the bathroom scale, imagine, if you will, that I had a bathroom scale that could measure picograms difference in mass. That's a sensitive instrument, right? A bathroom scale that only measures Cormac when he steps on it, and everyone else it doesn't read, is a specific bathroom scale, right? Does that make sense? As far as methods go. So atomic absorption is a specific method in that I don't measure a bunch of different elements. I measure one. And if I'm looking for one thing and I fit right, typically I do it better than measuring everything. That's kind of true in analytical chemistry. If I'm measuring one analyte very specifically, I can kind of, use filtering, use other methods to reject other sources of noise, other types of false positives, and be very specific, right? It's like if you go into the doctor and you're like, I don't feel great. They run a battery of tests, right? And maybe they'll find it. But if you walk in, your doctor goes, COVID, and does a COVID test, that's a very specific test, right? Maybe you don't have COVID, maybe you have the flu, right? Let's say in that case. So it's a specific method. You measure one element. Which element do you measure? Well, when you care about it, right? Not to put a fine point on it. But let's think about this. We still need gas phase atoms. All of atomic spectroscopy requires atoms in the gas phase, which we established Monday is not how atoms like to exist. The conducting elements of my iPad screen are made out of indium tin oxide, right? It's a material, right? It's a semiconductor. It's got indium and tin and oxygen, none of which are in their base zero gas phase redox state, right? I have to vaporize them and atomize them. So I still need to atomize. So I need a good bit of energy. The atom source requires heat.
Dr. Pappas?
Yeah.
I had a quick question. For the glow discharge, is the cathode made out of the sample?
It certainly contains it. Yeah, the cathode is your sample. So in other words, if you're analyzing, it's great. If you're analyzing a microchip to see the layers of material, the microchip is actually what the sample, it's electrically connected as the cathode in that case. Yes. Yeah. Good question.
Okay, so the cathode isn't just a container, it's the sample itself?
It is the sample, yeah, exactly.
Okay, awesome.
In theory, you could put your finger on it. I wouldn't because it's under high vacuum, but you could do glow discharge of tissue. I guess it would be a really bad idea on yourself or anyone you know. Or certainly anything with the spinal cord. All right. So atomic emission, right? You need high heat. But let's think about the Boltzmann equation for a minute. We just wrote it a minute ago. Do we want a large ratio of excited state to ground state atoms or a small one? So I'm just going to draw two states, right? We've got 0 and 1. In this case, we're absorbing a photon from the ground state to the excited state. So just intuitively, do you want the majority of your analytes populating the lower state or the upper state in question? What do you think? You say upper state? Is that you, Duncan? Did you say upper state? No. But what made you think that? I'm just curious. To emit down to the ground state? Well, here's the thing. In atomic absorption, we don't measure the emission. We don't care what happens to the atom after it's absorbed energy, right? Because we're measuring how much energy it took from the light source. What happens to it afterwards, whether it emits it as photons, whether it collides with something else and relaxes the ground state, is to us irrelevant, right? We only care about the absorption event. So, and actually, even in that case, I'll put it to you this way. The absorption event takes you from the lower state to the higher state, correct? So an atom that's already in the higher state has what probability of absorbing a photon to go from the lower to higher state? It's actually 0. It is. If I may, imagine, if you will, that the students, the heroes without capes who are in lecture today in person, are in the excited state. And my students on Zoom, and I'm just messing with you guys on Zoom, don't get panicky, all right? But the students on Zoom are in the ground state, if you will, right? Andrea, what is the probability of you right now leaving your apartment and coming to class? 0, because you're here, right? But maybe someone in the Zoom room is like, I better get in the car and get to class before it's over. That Dr. Pappas sees my face and thinks I'm a serious student, right? And I'm just messing around with you guys about that, but do you understand what I'm saying? Like, if it's already in the excited state, it has 0 probability of going to the excited state. It's already there. So an atom in the excited state cannot absorb a photon until it relaxes to the ground state again. So in a time-based snapshot, we want a low ratio of N1 over N0 for atomic absorption. In atomic emission, it is the opposite. We want a large ratio of excited state atoms because that's where the signal comes from, right? I'm probing the excited state in atomic emission. I'm probing the lower state or the ground state in atomic absorption. Now we're going to get into some nebulous territory. We want a source to do this, right? To get a low source, we need, yes, Alden. It's never the majority. Yeah. You just want a larger value of N1 over N0. It is very difficult to attain temperatures. In fact, if you think about it, you look at the equation, to reach, for example, an equal level of N1 over N0, you have to have the temperature, the energy from the heat has to approach the energy of a photon. That's very difficult to do. It's actually impossible to do on our planet, right? So you never, we're talking about maybe like a 0.1% ratio for atomic absorption and a 5% ratio for atomic emission, right? One's 50 times bigger than the other, but they're still pretty small, right? If you got a 5% in my class, no one's doing that bad, but if you got a 5% in class, and let's just, I'm just going to use names. Let's say that Shah got a 5% in my class. You're not going to, I know, right? And Misty's like, I got a 0.1% in the class. And you're like, haha, I'm 50 times better. But you both got Fs, right? Like super Fs. There aren't enough minuses, right, at that point. So we're still talking about a very small number, although I'm glad you brought that up. But relative to each other, we want a smaller ratio of N1 over N0 for atomic absorption. That is one of my favorite test questions in this course. Dun, dun, dun. Right? Sometimes I wonder if y'all learn anything or if you're just entertained, or neither. But I'm just going to keep doing what I'm doing because no one can stop me. Maybe you're learning. We'll see. I feel like that movie Gladiator. Like, are you not entertained? Like, are you not learning? But maybe you are. Okay. So now, when we're talking about having a lower ratio, this is like, students sometimes ask me, what's the right temperature for atomic absorption or atomic emission? The answer is kind of it depends, right? The sample matters, things like that, right? But in general, we're not going to use plasma sources for atomic absorption because they're very high temperature, right? They're good for emission. So I want a source that is hot enough to atomize, but cool enough to not populate the upper state appreciably, right? When I'm talking about cool enough, I'm talking about the low 2000 Kelvin range. Still effing hot, right, for our perspective. So we use flames. They're still used as common atom sources for atomic absorption because they're kind of cold. I once made a hydrogen argon flame in the lab, and it was like 1800 Kelvin when I was a grad student. And my Russian postdoc I worked with was like, "That's a cold flame, Dima." And I'm like, "It's 1800 Kelvin. Like, seriously, put your hand in it." I mean, don't, but you know. But he was just so excited. You couldn't even see it. It was so cold, quote unquote, that you had to put on like infrared goggles. And it's like, oh, there's a flame right there in that Bunsen burner, right? So, I mean, it's still hot though. So there are a bunch of different flames you can have, right? And they all need a fuel. And they all need an oxidant. This is GenChem, right? And they create a bunch of different temperature ranges, but you can have like hydrogen, argon, my favorite. We'll put this in Celsius because my notes are in. You can have hydrogen and air. This is in your notes too. I'm not going to go through all of them. You can go to acetylene and air, for example, much hotter. But and you know what's really good is oxygen by itself. It's a much better oxidant, as the name implies. In fact, if you're bored this weekend, YouTube barbecue grill liquid oxygen. Some MIT scientists poured liquid oxygen on their barbecue grill to see if it would burn hotter. It did. It's pretty great. Okay. And the flame burner is a little bit different than what you used in atomic emission in GenChem. It's actually 10 centimeters long. It's actually like a slot burner. So it looks like this. Like there's like an aperture, if you will. And this flame that's produced is 10 centimeters long, like a sheet. And the light from your hollow cathode lamp goes through it. The reason that we use a 10 centimeter long flame is that Beer's law tells us, I'll put it in quotes because it never really works this way. You all remember Beer's law, right? That absorbance is the product of the absorptivity, the path length, and the concentration. So for the absorptivity is a constant for the analyte in question, at the wavelength being measured, correct? That's just a constant. You measure this in Gen Chem. I know this because my freshman daughter and I got into a mild argument, it was not mild, about calculating this on her lab data a few weeks ago, where I may have uttered, I have an epic PhD in this, don't question me, or don't ask me for help, and then I stormed out of the room. It's a proud parenting moment right there, right? It was horrible. But we use a longer path length because if you have a longer path length for a given concentration, you get more absorption. And that actually is true in Beer's law. It's not necessarily linear, but it does happen that way. We're going to talk about Beer's law and why it's garbage later. Okay. The last atom source I want to talk about is the electrothermal atomizer. So these are just things you're going to find in the world. And there are a lot of different sources for atoms, but I would say if you're going to get a job and be asked to do atomic spectroscopy, you're going to either have glow discharge, an inductively coupled plasma, a flame, or an electrothermal atomizer, also known as a graphite furnace, by the way, in vernacular terms. It's a graphite tube with a hole in it and windows. Sorry, graphite tube. What do y'all know about graphite in general? It does turn into diamonds. What's it made out of? Carbon, right? Sheets of carbon that are pi conjugated. So they conduct, correct? You can actually write circuits out with a pencil, right? And that's what we use. Yes, Rebecca. Graphite furnace, yep. Yeah, no problem. I just like teaching this class so much, my pen can't keep up with my mouth. My brain's already like on Friday's lecture in my mind. All right. So graphite's conducting. So I pass a high current through it, right? So I put a voltage across it, and I pass a current through it. And this is a resistor. And so when you apply voltage to a resistor, you pass current through it. And what is generated as a waste product? Anybody have like toast this morning or a bagel? You did? Let's see. Did you make it in a toaster oven or toaster? What? In a toaster, right? So you applied a voltage across a resistor, and heat was generated, and then you had a toast, right? Same exact. It's just Ohm's law, right? So if I pass current through this device, I generate heat, right? This is how your oven works. Unless you have an induction stove, is how your stove works. You've been making food with this exact technology your whole life, right? If you put a resistor and you put a voltage across it, it's going to get hot. Okay, it just happens. So we use this as a way of generating heat in the graphite furnace. We heat up this graphite tube by putting a high current through it. The beauty of that is the temperature of a plasma depends on the flow rates of the gas into it and the power you apply, but it's not super controllable. A flame temperature depends on the reaction flow rates of the fuel and the oxidant and their chemical nature. So I can slightly adjust an air-oxygen or an oxygen-acetylene flame based on their flow rates, but that's it. In the case of the graphite furnace, I can control its temperature from room temperature all the way up to a few thousand degrees Kelvin. Yes?
So it's just that's off.
I mean, it's a small enough graphite furnace, it's pretty much uniformly distributed. And it takes some time to reach those temperatures, so it equilibrates pretty quickly. So that's a good question, though. So you put a drop of sample in the tube. You actually like deposit it. In the other cases, you flow in, constant stream of reagent. In this case, I put a known amount, and then I create a cloud of atoms as I heat up, right? Because this is temperature controllable, I can control N1 over N0 with greater precision than I can with the flame, right? So I can have a colder, blazing hot source, if that makes sense, okay? It's got a lot of advantages to it. It's more sensitive than other atom sources for absorption. One of the reasons for that is we have what's called a long residence time, long atom residence time. In other words, in a flame, okay, y'all did the emission flame test, right? Everyone did it. I want you to go back to your freshman days. You were younger, you weren't paralyzed with crippling self-doubt. It's a happy time, right? College is still exciting. When you had that loop with your salt solution on it and you put it in the flame, it changed color, right? You saw the emission of the material. When you removed the loop, what happened to the flame emission? Did it change back to the flame with itself, or did the atoms still stay in that flame and hang out and give you a lot of signal still? Take yourself back to that time. Do you not remember? It went back to normal, yeah, absolutely. Once it's gone, it's gone. In this case, the atoms hang out in this tube and just kind of float around, and then your light comes through and you measure absorbance, so you can measure it multiple times. Andrea, you're married. For 3 years now, you said? How long did y'all date before that? 4 years before that? Were y'all high school sweethearts? Aw, sweet. It really is. I'm not being sarcastic. That's really sweet. So you knew your husband, right? Pretty well. Because you interact with him a lot, right? So, like, you knew that maybe he doesn't like to clean the bathroom. Or, like, there are, like, quirks. As you know somebody, there are things that pop out. Misty, you've been married for a while, right? You know. She's like, oh, yeah, I know, right? There are things about your spouse. Ask my wife sometimes if you've ever seen in public. She'll, like, spend hours telling you about my many bizarre personality quirks, right, that I think make me endearing, but she would probably argue otherwise. Because you measure something longer, you know it more. You know it better, right? So the same atom that's floating around can absorb light and then return to the ground state and absorb again and return to the ground state. So you get basically more absorbance because the same atoms are absorbing repeatedly. Does that make sense? The longer, in general, in analytical chemistry, the longer you measure something or the more interaction with it that you have, the more information you can get out of it, and therefore usually the lower concentration or the better resolution. Right? That'll be a recurring theme in mass spectrometry, where we can trap ions in some case, and when we can do that, we can get incredibly precise measurements. Okay, so the longer residence time makes it more sensitive, right? You can handle complex samples, like blood. And because the temperature is voltage controlled, you can do temperature control. So you could do things like for blood, just for example, right? Anyone ever handle blood? Come to my lab and you have it. I have an entire refrigerator full of human blood. Like, people come through lab tours and we open it and they're like, what? And I'm like, yep, blood, just blood. Vials and vials of it. It looks gruesome. Blood is a pretty nasty material from an analytical chemistry standpoint. I mean, take out the infectious disease aspect of it, which is not insignificant, right? I mean, every time I give my students a vial of blood, like, this could kill you. Not in a, exploded in a blaze of glory and took the building with me kind of way, but more of a, you're going to die for 5 years straight in a horribly excruciating death. Be careful, right? Blood is viscous. It's got a solid component to it, right? It's a complex sample. I could take blood in a graphite furnace, and what I will do first is dry it at about 100 degrees Celsius, right? So I'll go up to about 100 degrees Celsius, and I'll remove water vapor, right? I'll remove the major constituent of blood. Then I can do another step at a couple hundred degrees, let's say 200 to 300 degrees C. That's called the ashing step, where I literally burn the organics into ash, right? Anyone that owns a pellet smoker, you do this, like, you have like a high burn to like remove the last thing you smoked in your barbecue. Same exact concept, right? Then you do actual atomic absorption. At whatever temperature, 2,000 to 3,000 Kelvin probably, or Celsius. Let's say Celsius. We'll stick with Celsius for now. They're not that different at these kind of temperatures. So you're able to take a raw sample run it in a step. Now, the downside is that's just to do one sample, right? So you do 3 different temperatures at 3 different times. Then you need to do the next blood sample. Well, you have to go back down to like room temperature, right? Or whatever temperature you start off with. And that takes time, right? But I can directly measure analytes. When the U.S. military measures lead poisoning in school-age children, like the Army does this as part of their outreach, they'll actually have graphite furnaces, like mobile systems, where they just spot it in there and they're just measuring lead, right? And because of that, they have a lead hollow cathode producing the emission light, and they just measure lead all day, every day. It's a very specific test, right? Now, I want to move on to something that I find more interesting, and that's molecular spectroscopy. The reason I find it more interesting is, first off, I don't need to produce gas phase molecules, so I can measure things in their native habitat, if you will. But also, if you think about all of the things, all of the matter that you learned about in chemistry in your 4+ years at Texas Tech, how many elements are there, roughly? Roughly about 120, right? 118, I think, currently. I guarantee we're not going to double that number. Right? We are approaching the absolute number of known elements in the universe that are stable. How many molecules have you learned about? More than 118? Organic chemists just put a chloride on something and go, now it's something else. And they write a paper about it, right? Then they're like, now it's a bromide, publish it. Now it's fluoride, publish it, right? I mean, right? Oh, this one's got a double bond. Totally different than the last one. And they are different. Let's take one of those and make it a really long version of itself. Polymers, right? You know that there are many more molecules out there as far as types and species, if you will, than there are elements, right? So that's a bit more interesting. And if you think about all the stuff that you've learned on in all of your classes, most of the things that you learned about are made out of what few number of atoms, right? Carbon, hydrogen, oxygen, nitrogen, sometimes sulfur. That's the majority of what you've looked at, correct? So the possibilities, it's like playing with Legos, right? There are some specialty pieces that have to be made because otherwise it won't look like a TIE fighter. But mostly we use 2x4 flat things to make stuff, right? I mean, I've got like millions of Legos in my home. I have children. They're not just mine, right? Some of them are mine. And, I use the same sort of basic pieces to build things, right? So molecular spectroscopy is much more diverse as a result. And I want to start off with absorption. And my nemesis, Spear's Law. Interestingly, it's also known as the Beer-Lambert Law, correct? You've heard that before? It's actually called the Beer-Lambert, some other guy no one remembers law. When you are inventing something, make sure you are the first author, because no one remembers it past that, right? Who was the first person to fly across the Atlantic Ocean? Anybody know? Charles Lindbergh. Anybody know the second person? I'll give you a hint. Her pronouns were she, her, hers. Anybody know? Amelia Earhart. Anyone know the third person? No. Right? You have to be the first, and that's it, right? The first or the first of the other team of whatever choice, right? Like the first American in space versus the first Russian in space, right? That kind of thing. Anyone know the first female astronaut in the U.S. space program? She's a scientist, y'all. Shame on you. Sally Ride. Ladies in the class, you should know that. Come on. She's a pioneer. She literally went into space, so you better have equal pay and be here today, right? So Beer, Lambert, other guy law, right? You all know that we measure absorbance, right? We do not measure absorbance. I have never measured absorbance in my life, and neither have you. Right? That's a B. It's a crappy B. We measure transmittance. And you might be thinking, well, Dr. Pappas, that's semantics. And it's not. You're wrong. Okay? Transmittance, if you remember, you've got a sample. I don't care what that sample is. It could be a test tube. It could be a cuvette. It could be a gas cloud in space. It doesn't matter. And you've got photons coming in at some incident intensity, correct? and then a smaller number of photons is transmitted out of there, right? This is the actual experiment. How do you measure I0? Well, you put a blank in place of the sample, that gives you I0. Then you put your sample in, and that gives you I, right? And you measure transmittance, which is the ratio of the transmitted over the incident intensity. You can put that in percent transmittance if you feel like it. It's the same thing. Oops. All right. Just times 100. All right. And then we told you, we wrote down Beer's law in class. Maybe Dr. Casadante did it, maybe Dr. Galeen, I don't know, whoever you had, Dr. Pasolino, all great professors. You know that you get absorbance by taking the negative log of transmittance. You've all done this, right? Yes. And then we told you that, and I just told you earlier in class, that it's the product of the absorptivity, which is a constant for that wavelength and for that analyte, times the path length, B, times the concentration. So if you double the concentration, you double the absorbance. If you make the path length 10 times longer in a flame, you get 10 times the absorbance. Except it doesn't. And I mentioned this before, using my same analogy. If I drop a brick on a duct, that brick always impacts that duct, right? That's cruel. I would never do that to a real duct, but or any. Nazis, maybe, I guess. I'm not a fan. Beer's law has all kinds of cases where it doesn't work. I can name time after time where changing the path length does not increase absorbance, or changing the concentration does not increase absorbance, right? There's actually, it requires a lot of caveats, right? Let's look at reality about Beer's law. Have you ever actually looked at a law that you learned in class and discussed all the assumptions that are made for it to be true? Are there any other laws that we've talked about in class besides Beer's law? The ideal gas law. That one works with an ideal gas, doesn't it? It's kind of hedging your bets a little bit because it's the ideal gas law, but it does work. Hooke's law works. Newton's 3 laws all work. If you don't believe me, stand on a boat, a small boat, and jump off of it and see what happens to the boat, right? Or don't do this, stand on a rolling chair and just wait for yourself to fall down, right? You will do it, right? So we know that all these other laws work, and we never sit in class. I promise, when you take like senior level physics, they're not going to go, just kidding, gravity actually doesn't work when in the following conditions, right? So the reality of Beer's law is the following. Absorption is not linear with concentration. Absorption is not linear with path length. Absorption requires monochromatic sources. Well, this is stuff we've never talked about in general chemistry. You ever thought about the monochromaticity of your light source in your absorbance instrument? In other words, that the wavelengths of light you're using to probe the sample are narrower than the absorbance band itself. Have you ever measured that? Did they tell you to do that in Gen Chem? No. They said turn the dial to 580 or whatever number and measure the absorbance, correct? And you did it like dutiful students that you are, correct? Excellent. Nothing else must absorb at that wavelength that you're measuring. That seems kind of intuitive, right? There should be nothing else in the sample that is also absorbing at the wavelength you're trying to measure. Do you know that it is? Unless you make a perfect blank that contains every constituent of your sample except for the analyte, you don't know that, okay? And we measure transmittance, right? Extinction. What we call extinction in optics. How do you spell extinction? Don't tell me. Just having a extinction, not absorbance. What do I mean by extinction? I've got some sample and I've got I0 coming at it, right? And I've got a sample. And then I have less coming through, right? That's the transmittance experiment. And we tell you that why does the light go down? Because it's being absorbed by the sample, by the atoms or molecules of interest. The analyte, right, is absorbing photons. I'm going to get a little... You can see me, right? How about now? No? For those of you on Zoom, I just crouched behind the lectern like a complete lunatic. This object absorbed light, right, that was reflecting off of me so that she could no longer see me. But what if I put a giant mirror between me and Michaela? Would you see me? A giant mirror right here. Would you see me? Now I'm behind it? No. Is that mirror absorbing light? Is it? If it's a perfect mirror, the world's greatest, most beautiful mirror, and it had perfect reflectivity, if I put a perfect reflecting mirror that's larger than me in front of me and stood here lecturing, how many of you would see me? None of you. Yet that mirror does not absorb light. So what's happening? It's reflecting, right? So in extinction literally means the reduction of light as it travels through something. Okay? You have several things going on. You have absorbance, you have reflection, and you have scattering, which is random. Scattering off of particles. All of these things occur at the same time. Extinction, which is really I over I0, is the sum of absorbance and scatter and reflection. Now, reflection is usually not an issue in our samples. Well, let's say you're measuring a compound in urine. Urine has particulate matter in it. And depending on your soda intake more than others, right? Your salt intake more than others. And so there's actually like light scattering that occurs. I'm going to give you the greatest example of living in Lubbock. Dust storms. Remember that dust storm we had like 2 weeks ago? It's like hell opened up. It was watching like the Mummy, right? Could you see very far? Was visibility good? No. We had one a couple years ago that was so bad that like I couldn't see my car in the driveway. My kids were like, it's like Mars! And they were like putting on stuff to play in, and I'm like, you're all asthmatics. Sit your immune compromised cells back down and play some Nintendo. If you're not going outside, you're all gonna die, right? I don't normally care about my kids' asthma, but they're not coming back from that one. You know that in a Lubbock dust storm, you can't see anything, but there's no absorbance going on. It's all light scatter, right? The particulate matter in the air is scattering light. But if you did an absorbance measurement that day of air, it would be sky high, even though no absorbance is happening, right? So we're going to talk about how to get around these assumptions to make Beer's law accurate, and then the instrumentation of UV-Vis light measurements. But just understand that Beer's law, these assumptions are never, like these assumptions right here, are never, ever, 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 ever checked in real life. People are lazy. And so when you have an absorption measurement, you actually can't trust it unless you do a little bit extra work, okay? I will see you all on Friday. Have a good day.
Dr. Pappas?
Yep.
I had another quick question. Sorry about that.
No, please ask.
So for atomic absorption, you said we wanted a small ratio of N1 to N0 for atomic absorption?
Correct.
And a large one for emission, right?
Yes.
Okay, and then there was another thing you said. It was we're probing the ground state in absorption, probing the excited state in emission.
And that's why you need a larger N1 over N0 for emission, because it's actually looking at atoms in that state.
Oh, okay, awesome. All right,
Yeah.
thank you.
No problem. Thank you. Bye. What's up?